Welcome back. We're still in example 1 and part C here. We're still trying to prove that one of these rules works by plugging in 150 degrees for A and 120 degrees for B. So if we look at the tangent of A minus B equals the tangent of A minus the tangent of B over 1 plus the tangent of A times the tangent of B, we can plug those in first. The tangent of 150 minus 120 is going to be the tangent of 150 minus the tangent of 120 over 1 plus the tangent of 150 times the tangent of 120. Now this one's going to take a little bit of space here, so I might work horizontally for a little bit. The tangent of 150 minus 120 is really the tangent of 30, just by subtraction. Now it's easier to look at. The tangent of 150 is negative root 3 over 3, or negative 1 over root 3, minus the tangent of 120 is negative root 3. All that is over 1 plus the product of those two tangents, negative root 3 over 3 times negative root 3, which is technically negative root 3 over 1. Let's simplify this a little bit. Let's take the top part separate from the bottom part and simplify them by division as well. We can also look at a few things here. So we're subtracting negatives a few times. So minus a negative becomes plus a positive. Negative times a negative will become a positive, and root 3 times root 3 is actually just going to be 3 over 3. So we're really looking at negative root 3 over 3 plus root 3 divided by 1 plus 3 over 3. And again, we can simplify a little bit more, partly by making common denominators, and partly by simplifying the fractions, because 3 over 3 is actually 1, and 1 plus 1 we can figure out pretty quickly. If we multiply by 3 over 3, we can make common denominators here. So we're really looking at negative root 3 over 3 plus positive root 3 over 3 would make 2 root 3 over 3 divided by 1 plus 1 is 2, or 2 root 3 over 3 times 1/2, where the 2's can now cancel out. And now we'll go back down where we have root 3 over 3, which, if we look at our unit circle, the tangent of 30 is also root 3 over 3. So the rule works because that thing is itself. So how are you actually going to use these sum and difference formulas? You're going to use them with the unit circle to find the sines and cosines, the exact values, again with radicals and everything, of some maybe unfamiliar numbers that are not on the unit circle. For example, the cosine of 105 degrees or the sine of 105 degrees. Well, neither of those is really a familiar number from the unit circle, but you can break down 105, and now we're looking at the cosine of 60 degrees plus 45 degrees. And now we can use that cosine of A plus B rule. So that would be cosine, cosine, sine, sine is the pattern, and we switch our plus to a minus when we expand. So the cosine of 60 degrees times the cosine of 45 degrees minus the sine of 60 degrees times the sine of 45 degrees. I'll try not to bleed into the sine one too much more. So If we simplify this side by looking at the unit circle, again, all of this is really the cosine of 105, which we're trying to find. The cosine of 60 is 1/2. Cosine of 45 is root 2 over 2. Minus the sine of 60 is root 3 over 2. Times the sine of 45 is root 2 over 2. So we simplify the fractions by multiplying straight across. 1 times root 2 is root 2 over 2 times 2 is 4 minus root 3 times root 2. Those are both roots, so we can just multiply those to make root 6. They are a like term in that way. We can multiply by we can multiply any two radicals by each other to simplify over 4. And now we have some common denominators. We need to make a single exact fraction out of this, but the problem is we can't actually subtract root 2 from root 6 or root 6 from root 2. We don't know precisely what that would be. You can multiply radicals together, but unless they are the same number underneath the radical, the most we can do with this is say it's whatever root 2 is minus whatever root 6 is, and both of those are over 4. And that is the exact value of the cosine of 105 degrees. Next, we'll look at the sine of 105 degrees, which again, we looked at how 105 is really the sine, or sorry, the 105 is really 60 plus 45 in the last example. And the pattern for sine is sine, cosine, cosine, sine, AB, AB. So the sine of 60 degrees times the cosine of 45 degrees plus, because you can keep the same sign as the sine. The cosine is the opposite. It's the complement to whatever it said. So the complement of plus would be minus, I guess. That's not really proper use of the vocabulary, but it kind of helps. Or it helps me. Anyway, times the cosine of 60 degrees times the sine of 45 degrees. So again, looking at our unit circle, I'm just getting that the sine of 60 is root 3 over 2 times the cosine of 45 is root 2 over 2 plus the cosine of 60 is 1/2, and the sine of 45 is also root 2 over 2. So root 3 times root 2 is again root 6 over 4 plus 1 times root 2 is root 2 over 4. And again, we can't really do much more than say that this is the square root of 6 plus the square root of 2, but all of it is over 4. If you wanted to reorder that to make the root 2 come first, you can. Generally, though, if there's a plus in between, you don't necessarily have to do descending order or anything with the radicals. It might, you could also say for part A, this could have been negative root 6 plus root 2 if over 4 if you really wanted to, but you didn't really have to. All right, the tangent of 105. Tangent of 105 is really the tangent of 60 plus 45. And again, tangent, the top has the same sign as whether we're adding or subtracting. The bottom is the opposite. So we're really looking at the tangent of 60 degrees plus the tangent of 45 degrees over 1 minus the tangent of 60 times the tangent of 45. Looking at the unit circle, the tangent of 60 is just the square root of 3. Tangent of 45 is 1. Again, those are not like terms, so we can't really do anything to simplify beyond root 3 and 1. And again, looking at the unit circle, same things. 1 minus root 3 times 1. Multiplication here, 1 times root 3, 1 times anything is itself. So, can't really do anything at the top. Root 3 plus 1. Maybe we could say it's 1 plus root 3, just so the radicals come at the end. I'll do that in the next step. Over 1 minus root 3. Yeah, let's actually make that 1 plus root 3 over 1 minus root 3. So, next thing we need to do is rationalize so that we don't have a radical in the denominator. But unfortunately, we can't just multiply by the square root of 3, because if we do that, it'll distribute and we end up with another root 3 in the place of the 1. So in order to get this root 3 squared away, we need to multiply by 1 plus the square root of 3. Because again, we're using that rule where a plus b times a minus b can simplify to a squared minus b squared. That way the root 3, will get squared and go away from the bottom. We'll just have to multiply by 1 plus root 3 at the top. But again, that also looks like a shortcut pattern that I have. A plus b times itself, or squared, becomes a squared plus 2ab plus b squared. So, doing some of that FOIL work, we end up with 1 plus 2 root 3 plus 3 over 1 squared minus root 3 squared. One plus 3 here is 4 plus 2 root 3. 3 squared. 1 squared is 1, 3 squared is 3, and it's 1 minus 3, because remember, only the root 3 is getting squared here. There's no parentheses, so the negative is not really a negative sign, it's a minus sign. We're actually only squaring the root 3. It's also part of the pattern. So again, can't do much with the top, other than leave it as 4 plus 2 root 3 over 1 minus 3 is negative 2. Now we can start doing a little bit more, because it looks like we can factor out or divide each of these numbers by negative 2. We can make that something like 4 over negative 2 plus 2 root 3 over negative 2. 4 divided by negative 2 is negative 2. 2 root 3 divided by negative 2 is negative root 3. And that is the exact value of the tangent of 105. That was a lot, so we'll take the next 3 in the next video.